Welcome. Dear learner, we are discussing about the radioactive equilibrium. In previous lecture, we discussed about the ideal equilibrium and secular equilibrium. The equilibrium in which the activity of a parent is equal to activity of a daughter is known as the ideal equilibrium. The secular equilibrium is the equilibrium in which the parent live extremely longer time than the daughter. Then such type of equilibrium is the secular equilibrium. Friends, in this lecture we have to see what is a transient equilibrium. The equilibrium in which the parent live longer time than that of a daughter. Then such type of equilibrium is the transient equilibrium. The parent live longer time than the daughter, but it is not much more time, and therefore we can say that the half-life of parent is greater than half-life of a daughter, but it is not very greater than the half-life of a daughter. We know that the number of radioactive nuclei for a daughter atom, that is N2, it is equal to N0 lambda 1 divided by lambda 2 minus lambda 1 in bracket e raised to minus lambda 1 into t minus e raised to minus lambda 2 into t. Okay. This equation represents the number of radioactive nuclei of a daughter atom. Now, when we take a common e raised to minus lambda 1 into t from this term, we get n0 into lambda 1 e raised to minus lambda 1 into t, okay, in bracket 1 minus e raised to minus lambda 2 into t divided by e raised to minus lambda 1 into t, okay, divided by lambda 2 minus lambda 1, okay. Now this can be also written as n2, it is equal to lambda 1 into n0 e raised to minus lambda 1 into t divided by lambda 2 minus lambda 1. This term can be written as 1 minus e raised to minus lambda 2 minus lambda 1 into t. Okay? But we know that according to law of radioactive decay, the radioactive nuclei exponentially decreases with the time, and therefore the number of radioactive nuclei for the parent atom, that is N1, it is equal to N0 e raised to minus lambda 1 into t. Okay, this represents the number of radioactive nuclei for the parent atom, and therefore this equation became N2, it is equal to lambda 1 into N1 divided by lambda 2 minus lambda 1 in bracket 1 minus e raised to minus lambda 2 minus lambda 1 into t. Okay. Now multiplying both sides by lambda 2, multiplying both sides by lambda 2, we get n2 into lambda 2, it is equal to n1 lambda 1 n1 into lambda 2 divided by lambda 2 minus lambda 1 in bracket 1 minus e raised to minus lambda 2 minus lambda 1 into t. Okay. Now this term can be also written as N2 lambda 2 divided by N1 lambda 1. It is equal to lambda 2 divided by lambda 2 minus lambda 1 in bracket 1 minus e raised to minus lambda 2 minus lambda 1, okay, into t. The numerator represent the activity of a daughter, while denominator represent activity of a parent. Okay, we know that the half-life of a radioactive nuclei can be written as, for a daughter, that is T2, it is 0.693 divided by lambda 2. So lambda 2 it is equal to 0.693 divided by T2, and T1 it is equal to 0.693 divided by lambda 1. So lambda 1 it is equal to 0.693 divided by T1. When we put this value in this equation, we get N2 lambda 2 upon N1 lambda 1. It is equal to 0.693 divided by T2 divided by 0.693 divided by T2 minus 0.693 divided by T1 into, okay, 1 minus e raised to minus. Again, when we put the value of lambda 2 here, we get 0.693 divided by T2, okay, minus 0.693 divided by T1 into T. Okay. Now this term became T1 upon T1 minus T2. T1 minus T2. Here, this T is very large. T is very large, and therefore we can represent only this term. Okay, T is very large. Actually, here is 0.693 divided by T2 minus 0.693 divided by T2, 0.693, it get cancelled. But T is very large, and therefore we can represent like this. Okay. Now, this equation is good only when this T1 upon T1 minus T2 is greater than 1. Okay, it is greater than 1. Okay. And we can say that the equation is good, then the equilibrium is a transient equilibrium. Okay, if T1 upon T1 minus T2, it is greater than 1. If we consider one example, Ba, okay, that is a barium 140. Now this barium 140 is converted into lanthanum 140. Okay, lanthanum 140. And this is in 300 hours. So T1 is equal to 300 hours. That is, this is the half-life for which the barium is converted into the lanthanum. Okay, this is a beta decay. Now the lanthanum is converted into the cerium. Okay, that is a Ce 140 in 40 hours. Okay, barium 140 is converted into the lanthanum 140 in half-life is about 300 hours. This lanthanum is converted into the cerium, which is the stable end product, and the half-life is about 40 hours. Here we can say that the parent live longer time than that of a daughter. Okay, here half-life is a 300 hour and here is a 40 hour. But it is not much greater than the lifetime of a daughter. Okay, it is not much more. Then such type of the equilibrium is known as the transient equilibrium. Now we have to find this ratio. This equation is good. Okay, only when time t is very large and T1 upon T1 minus T2, this ratio is greater than 1.